Hey you all, did you know that everything you see, touch, and experience, every object, every person, every star in the night sky, might actually be just a shadow of something far more complex? That the three dimensions we take for granted, length, width, and height, could be only part of a much richer reality. For centuries, scientists and philosophers have wrestled with this idea. And today, modern physics suggests that our universe might not stop at three dimensions at all. In fact, some of our most promising theories about how the universe works require extra dimensions, dimensions so tiny or so hidden that we've never noticed them yet. Now, before you roll your eyes and think this sounds like science fiction, hear me out. This isn't wild speculation. It's serious science, grounded in mathematics and tested through logic, observation, and experiment. The idea of higher dimensions isn't just a neat trick to make equations work. It could be the key to unlocking the deepest mysteries of the cosmos. Why gravity is so weak compared to other forces, what happened at the very beginning of time, and whether all the fundamental forces of nature are really just different faces of one unified force. So in this video, we're going to explore a simple but profound question. Do we really live in three dimensions? To answer it, we'll journey from the familiar world of everyday experience into the strange realms of theoretical physics. We'll talk about how mathematicians first imagined spaces with more than three dimensions, how Einstein changed our understanding of space and time, and how string theory, the leading candidate for a theory of everything, demands that the universe have not 3, not 4, but 10 or even 11 dimensions. And don't worry, we won't drown in symbols or abstract jargon. I'll explain every concept clearly, using words instead of equations whenever possible. But when formulas are essential, I'll write them out fully in plain English, just as you asked. So if you've ever looked up at the stars and wondered whether there's more to reality than meets the eye, you're in the right place. Let's begin. First, let's get clear on what we mean by a dimension. In everyday language, a dimension is just a direction in which you can move or measure something. In our normal experience, we have three spatial dimensions. You can go left or right, that's one dimension, often called the x direction. You can go forward or backward, that's the second dimension, the y direction. And you can go up or down, that's the third, the z direction. With these three directions, you can describe the location of anything in space. Your coffee cup is 2 feet in front of you, half a foot to the left, and sitting on the table, which is, say, 3 feet off the ground. Three numbers, three dimensions. But here's the thing. Nothing in our basic understanding of physics says there can't be a fourth spatial direction, one that's perpendicular to all three of the ones we know. Perpendicular means at a right angle. So just as up-down is at a right angle to left-right and both are at right angles to forward-backward, a fourth dimension would be at a right angle to all three of those simultaneously. Now, try to picture that. Go ahead, I'll wait. It's impossible, isn't it? Your brain just doesn't have the hardware to visualize a direction that's completely orthogonal to the three you live in. But that doesn't mean it can't exist. After all, a two-dimensional being living on a flat sheet of paper couldn't imagine up either. To them, the idea of a third dimension would seem absurd, until someone lifted them off the page and showed them the bigger picture. This analogy was famously explored in a book called Flatland, written in 1884 by Edwin Abbott. In it, he imagines a world inhabited by geometric shapes, triangles, squares, circles, all living on a flat plane. They have no concept of height. To them, the universe is strictly two-dimensional. Now suppose a three-dimensional sphere passes through their flat world. What would they see? At first, nothing. Then, as the sphere begins to intersect the plane, they'd see a point appear out of nowhere. That point would grow into a small circle, then a larger circle, then shrink again until it vanished. From their perspective, it would look like a mysterious object materializing, changing size and disappearing, without any cause they could understand. But to us, watching from above, it's perfectly clear. It's just a slice of a sphere moving through their plane. Now flip that around. What if our three-dimensional world is just a slice of a higher dimensional reality? Could objects or forces from a fourth spatial dimension be interacting with our universe in ways we can't directly perceive, but might detect indirectly? That's not just philosophy. That's a real possibility in modern physics. Let's step back for a moment and look at how the idea of extra dimensions entered science in the first place. It didn't start with string theory or quantum gravity. It actually began with an attempt to unify two of the fundamental forces of nature, gravity and electromagnetism. In the 1920s, a German mathematician named Theodor Kaluza had a brilliant insight. He noticed something strange. If you took Einstein's equations of general relativity, which describe gravity as the curvature of spacetime, and wrote them down in 5 dimensions instead of 4, 3 of space plus 1 of time, something remarkable happened. The extra components of the 5-dimensional curvature equations looked exactly like Maxwell's equations for electromagnetism. In other words, by adding one extra spatial dimension, gravity and electromagnetism seemed to emerge from the same geometric framework. That's huge. It suggested that what we experience as two separate forces might actually be two aspects of a single, unified force, manifesting differently because of the shape of spacetime itself. But there was a problem. If there's a 5th dimension, why don't we see it? Kaluza's student, Oskar Klein, proposed a solution. He suggested that the extra dimension might be curled up, so tiny that it's invisible to us, like the thickness of a garden hose. From far away, a hose looks like a one-dimensional line, but if you get close enough, you see it has a 2nd dimension wrapped around its circumference. Similarly, maybe every point in our 3-dimensional space has a tiny, circular extra dimension attached to it, so small that even our most powerful microscopes can't detect it. How small? Klein estimated it would be on the order of the Planck length, the smallest meaningful length scale in physics, about 10 to the power of -35 meters. That's a decimal point followed by 34 zeros and then a 1. Way smaller than an atom, way smaller than a proton. No wonder we haven't seen it. This idea, now called Kaluza-Klein theory, was largely forgotten for decades, partly because it couldn't explain the newly discovered nuclear forces, the strong and weak forces, and partly because quantum mechanics was stealing the spotlight. But it planted a seed. Extra dimensions could be real, and they could help unify the laws of physics. Fast forward to the late 20th century. Physicists were struggling to reconcile general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which governs the subatomic world. These two pillars of modern physics are incredibly successful in their own domains, but they clash violently when you try to combine them. At the center of a black hole, or in the first moments after the Big Bang, both theories should apply, but their predictions contradict each other. Something had to give, and that's where string theory came in. String theory proposes that the fundamental building blocks of the universe aren't point-like particles, electrons, quarks, photons, but tiny, vibrating loops of energy called strings. These strings are unimaginably small, again on the order of the Planck length, but their vibrations determine the properties of the particles we observe. One vibration mode gives you an electron, another gives you a photon, another gives you a graviton, the hypothetical particle that carries the gravitational force. Here's the kicker. For the math of string theory to work consistently, to avoid nonsense like probabilities greater than 1 or negative energies, the strings must vibrate in more than 3 spatial dimensions. In fact, the original version of string theory required 10 dimensions, 9 of space and 1 of time. Later, a more advanced version called M-theory pushed that number to 11 dimensions, 10 of space and 1 of time. So according to our best attempts at a unified theory of physics, the universe must have extra dimensions. But again, Why don't we see them? The answer goes back to Kaluza and Klein in string theory. The extra 6 or 7 spatial dimensions are compactified, curled up into intricate, tiny shapes called Calabi-Yau manifolds. These shapes are so complex and so small that they're completely hidden from our everyday experience. But they're not irrelevant. The exact geometry of these compactified dimensions determines the properties of the particles and forces in our observable universe. For example, the number of generations of elementary particles, the masses of quarks, the strength of the electromagnetic force, all of these could be consequences of how the extra dimensions are folded. Think of it like this. Imagine a guitar string. The note it produces depends not just on the string itself, but on the shape and size of the guitar's body. Similarly, the notes played by fundamental strings, the particles we see, depend on the shape of the hidden dimensions. Change the shape, and you change the laws of physics. Now you might be thinking, if we can't see these extra dimensions, how can we ever test string theory? That's a fair question, and it's one of the biggest criticisms of the theory. But there are indirect ways we might detect them. One possibility involves gravity. Of all the fundamental forces, gravity is by far the weakest. It's about 10 to the power of 36 times weaker than electromagnetism. Why? One idea is that gravity leaks into the extra dimensions. While the other forces, electromagnetism, the strong force, the weak force, are confined to our three-dimensional brain, short for membrane, a term used in string theory to describe our slice of the higher dimensional space, gravity can spread out into the full bulk of the higher dimensional space. As a result, its strength gets diluted in our 3 dimensions, making it appear weak. This leads to a fascinating prediction. At very small distances, smaller than the size of the extra dimensions, gravity should become stronger than expected. Normally, gravity follows an inverse square law. The force between 2 masses is proportional to 1 divided by the distance squared. But if there are n extra dimensions of size r, then at distances much smaller than r, gravity should follow an inverse 2 plus n law. So if we could measure the gravitational force between 2 objects separated by less than a millimeter, or even a micrometer, we might see a deviation from Newton's law. Experiments have been done to test this. Using exquisitely sensitive torsion balances, physicists have measured gravity at submillimeter scales. So far, no deviation has been found, which tells us that if extra dimensions exist and gravity leaks into them, they must be smaller than about 50 micrometers. But that still leaves room for dimensions that are microscopic but larger than the Planck scale, what are called large extra dimensions in the literature, large being relative, of course. Another way to probe extra dimensions is through particle colliders like the Large Hadron Collider. If extra dimensions exist, it might be possible to produce particles called Kaluza-Klein modes. Remember how, in the flatland analogy, a sphere passing through the plane creates a series of circles. Similarly, a particle that can move in an extra curled-up dimension would appear to us as a whole tower of particles with increasing masses. Each mass corresponds to a different number of wavelengths fitting around the compact dimension, like harmonics on a guitar string. So if we smash protons together at high enough energies, we might create these heavy Kaluza-Klein partners of known particles, say, a heavy photon or a heavy graviton. Their decay products would carry telltale signatures. So far, no such particles have been seen at the LHC, which places limits on the possible size and number of extra dimensions. But the search continues. Now, let's clarify something important. Not all versions of string theory treat extra dimensions the same way. In some models, all extra dimensions are tiny and curled up. In others, like the Randall-Sundrum models, there can be one large extra dimension, warped in such a way that it explains the weakness of gravity without requiring the dimension to be microscopic. In the Randall-Sundrum model, Our universe is a four-dimensional brain embedded in a five-dimensional bulk, spacetime. The fifth dimension is not flat. It's curved by a negative cosmological constant, creating what's called anti-de Sitter space. Because of this warping, gravity is exponentially suppressed on our brain compared to a second brain located elsewhere in the fifth dimension. This exponential suppression can account for the huge difference between the strength of gravity and the other forces, even if the extra dimension is relatively large, perhaps as big as a fraction of a millimeter. What's beautiful about this idea is that it solves the so-called hierarchy problem, the puzzle of why the gravitational scale, the Planck scale, around 10 to the power of 19 GeV, is so vastly different from the electroweak scale, around 100 GeV, where the Higgs boson lives. Instead of fine-tuning parameters to absurd precision, the warping of spacetime naturally generates the huge gap. But again, how do we test it? One signature would be the production of massive spin-2 particles called radions or Kaluza-Klein gravitons that decay into pairs of photons or leptons. The LHC has searched for such events, and while no discovery has been made yet, the parameter space is still being explored. Let's now return to the core question. Do we really live in three dimensions? Based on everything we've discussed, the answer is complicated. From the perspective of direct sensory experience, yes, we live in three spatial dimensions. All macroscopic objects, all forces except possibly gravity, all known particles behave as if space has only three extended directions. But from the perspective of fundamental physics, especially in the context of unifying quantum mechanics and gravity, three dimensions may not be enough. The mathematics demands more. And here's a subtle but crucial point. Dimensions aren't just places you can go. They're degrees of freedom in the fabric of reality. Each dimension adds a new way for fields to vary, for waves to propagate, for symmetries to operate. In quantum field theory, the framework underlying the standard model of particle physics, fields exist everywhere in space and time, and their excitations give rise to particles. If there are extra dimensions, those fields can also vary in those directions, leading to richer structures. For example, consider the formula for the acceleration of an object. In Newtonian physics, acceleration equals the net force acting on the object divided by its inertial mass. Written out in words, that's acceleration equals force pulled divided by mass inertial. This equation works perfectly in three dimensions, but if there were a fourth spatial dimension, forces could have components in that direction too, and the full description of motion would require four spatial coordinates. However, if that fourth dimension is compactified, the extra components would manifest not as new directions of motion, but as new types of particles or fields in our three-dimensional world. This is the essence of dimensional reduction, the process by which a higher dimensional theory appears as a lower dimensional one when some dimensions are curled up. The extra information isn't lost. It's encoded in the spectrum of particles and coupling constants we observe. Now let's address a common misconception. Some people hear extra dimensions and immediately think of parallel universes or alternate realities. But that's not what physicists mean. Extra dimensions in string theory or Kaluza-Klein theory are part of our own universe. They're just hidden from view due to their size or geometry. Parallel universes belong to a different idea altogether, like the many worlds interpretation of quantum mechanics or the multiverse scenarios in cosmology. Those are fascinating topics, but they're separate from the question of spatial dimensions. Another point of confusion: time is often called the fourth dimension. And in Einstein's theory of relativity, it's true that space and time are woven together into a four-dimensional continuum called spacetime. But time is fundamentally different from spatial dimensions. You can move freely back and forth in space, but you're always carried forward in time, at least in our current understanding. The metric signature of spacetime reflects this. In special relativity, the spacetime interval is given by the square of the time component minus the sum of the squares of the spatial components. So time isn't just another direction, it has a unique role. When physicists talk about extra dimensions in string theory, they're referring to additional spatial dimensions, not extra time dimensions. In fact, theories with more than one time dimension tend to be unstable or inconsistent, leading to paradoxes like closed time-like curves or violations of causality. So almost all serious models stick to one time dimension and multiple spatial ones. Let's now dive a bit deeper into the geometry of extra dimensions. What does it mean for a dimension to be curled up? Imagine taking a piece of paper, a two-dimensional surface, and rolling it into a cylinder. The paper still has two dimensions, but one of them, the direction around the cylinder, is now periodic. If you walk in that direction, you eventually come back to where you started. The size of the circle determines how big that dimension is. In Kaluza-Klein theory, the fifth dimension is like that circle, tiny and closed. But in string theory, the extra 6 dimensions are curled up into much more complicated shapes called Calabi-Yau manifolds. These are 6-dimensional surfaces with very specific mathematical properties. They're compact, Ricci-flat, and preserve a certain amount of supersymmetry, a symmetry between matter particles and force carriers. Why Calabi-Yau? Because they satisfy the equations of motion derived from string theory while allowing for chiral fermions, the kind of particles that make up matter in our universe, like left-handed neutrinos. Other shapes either break supersymmetry too much or don't produce the right particle content. The problem is that there are potentially millions, or even billions, of different Calabi-Yau shapes, each leading to a different set of physical laws in the four-dimensional world. This is part of the so-called landscape problem in string theory. If there are so many possible vacuum states, how do we know which one describes our universe? And if all of them exist somewhere in a multiverse, does that make string theory unfalsifiable? These are open questions, but the existence of the landscape doesn't invalidate the idea of extra dimensions. It just means the theory is richer and more complex than we initially hoped. Now let's consider an alternative viewpoint. What if extra dimensions aren't curled up at all? What if they're infinite, but we're stuck on a three-dimensional brane and can't leave it? This is the premise of brane world scenarios. In these models, the particles of the standard model quarks, electrons, photons, are represented by open strings whose endpoints are fixed to our brane. They literally can't leave it. But gravity, carried by closed strings, loops with no endpoints, can propagate freely through the entire higher dimensional bulk. This explains why we don't see extra dimensions in everyday life. Everything we're made of, and everything we interact with via non-gravitational forces, is confined to the brane. Only gravity knows about the full geometry of spacetime. One dramatic consequence of this idea is that microscopic black holes could be produced at much lower energies than previously thought. If the fundamental scale of gravity is lowered due to dilution in extra dimensions. At the LHC, if two protons collide with enough energy concentrated in a tiny region, they might create a quantum black hole that instantly evaporates via Hawking radiation. Such an event would produce a spherical burst of high-energy particles, an unmistakable signature. Again, no such events have been observed, but the possibility remains open at higher energies. Let's also talk about how extra dimensions affect cosmology. In the early universe, when temperatures were extremely high, all dimensions, compact and extended, might have been on equal footing. As the universe cooled, only 3 spatial dimensions expanded to macroscopic size, while the others stabilized at a tiny scale. Why did only 3 expand? That's another unsolved problem, sometimes called the dimensional selection problem. Some theories suggest it's due to dynamical instabilities or topological constraints, but there's no consensus yet. Interestingly, if extra dimensions change size over cosmic time, they could leave imprints on the cosmic microwave background or the distribution of galaxies. For example, variations in the size of compact dimensions would effectively change the values of fundamental constants, which might be detectable in precision astrophysical observations. Now let's bring this back to your daily life. Does any of this matter if you're not a physicist? In a practical sense, probably not. Your car, your phone, your coffee maker, all work perfectly well under the assumption of 3 spatial dimensions. But philosophically, it's profound. It suggests that reality is far stranger and more layered than our senses reveal. Just as the Earth isn't flat, just as time isn't absolute, just as particles can be in 2 places at once, our intuition about space itself might be incomplete. And that's the beauty of physics. It doesn't just describe the world as it appears, it seeks the world as it truly is, even if that truth lies beyond our immediate perception. Before we continue, let's recap where we are. We've seen that dimensions are directions in which things can vary or move. We experience 3 spatial dimensions directly. Mathematical consistency in unifying gravity and quantum mechanics requires extra spatial dimensions. These extra dimensions could be tiny and curled up, or large but inaccessible because we're confined to a brain. There are experimental efforts underway to detect signs of extra dimensions through gravity experiments, particle colliders, and cosmological observations. String theory, our most developed framework for quantum gravity, demands 10 or 11 dimensions. But we haven't yet fully explored what it would mean to live in a higher dimensional space. So let's imagine, for a moment, what life would be like if we could perceive a 4th spatial dimension. Suppose you're a 4-dimensional being. You could look inside a 3-dimensional object without opening it, just as we can look inside a 2-dimensional circle drawn on paper without crossing its boundary. A safe would offer no security to you. You could reach in and remove its contents from the outside. Knots that are impossible to untie in 3 dimensions could be trivially undone in 4. You just lift a strand into the 4th dimension, move it around, and drop it back. Even biology would be different. In 3 dimensions, your digestive tract is a tube that runs from mouth to anus. If it branched, you'd fall apart. But in 4 dimensions, you could have a fully connected internal network without compromising structural integrity. Your heart wouldn't need to pump blood in a loop. It could circulate fluid through a 4-dimensional volume. Of course, this is all speculation, but it shows how deeply the number of dimensions shapes the possibilities of existence. Now, here's a critical point. The fact that we can't visualize higher dimensions doesn't mean we can't describe them mathematically. In fact, mathematicians have been working with n-dimensional spaces for over a century. A point in n-dimensional space is just an ordered list of n numbers. Distance is defined by the generalized Pythagorean theorem, the square root of the sum of the squares of the differences in each coordinate. Vectors, derivatives, integrals all extend naturally to higher dimensions. Physics builds on this. The equations of motion, conservation laws, field theories, they all generalize. So even if our brains are limited to 3 spatial dimensions, our mathematics isn't. And that's how we can confidently explore realms beyond direct experience. Let's look at one concrete example, the formula for the gravitational force between 2 masses. In 3 spatial dimensions, it's gravitational force equals the gravitational constant times the product of the 2 masses, divided by the square of the distance between them. But in a universe with d spatial dimensions, the force would fall off as 1 over distance to the power of d minus 1. So in 4 spatial dimensions, gravity would follow an inverse cube law. In 5, inverse 4th power, and so on. This has observable consequences. For instance, planetary orbits would be unstable in more than 3 spatial dimensions. In 4 or more dimensions, there are no stable elliptical orbits. Planets would either spiral into the sun or fly off into space. The fact that we have stable solar systems is indirect evidence that large extraspatial dimensions don't exist on astronomical scales. But again, they could still exist on microscopic scales, where orbital mechanics don't apply. This ties back to why extra dimensions must be compactified or hidden. If they were large and flat, the universe would look very different. Stars might not form, atoms might not be stable, and life as we know it couldn't exist. So the very fact that we're here to ask the question may be a clue that extra dimensions, if they exist, are constrained in specific ways. In summary, the idea that we live in only 3 dimensions is both true and incomplete. True, because all empirical evidence confirms that space behaves as 3-dimensional at the scales we can probe. Incomplete, because our deepest theories of reality suggest that 3 dimensions are just the tip of the iceberg. Whether extra dimensions are real remains an open question, one that future experiments may answer. But even if they turn out to be a mathematical artifact, the journey to understand them has already reshaped our view of space, time, and the unity of nature's laws. And that brings us to the end of this first part. We've covered the historical origins of extra dimensions, their role in unifying forces, how string theory requires them, and the ways we might detect them. In the next part, we'll go deeper into string theory itself, what strings are, how they vibrate, why supersymmetry matters, and how all this connects to black holes, holography, and the nature of spacetime itself. But for now, take a moment to reflect. The next time you look around, at the walls of your room, the trees outside, the vastness of the night sky, remember, you might be seeing only a shadow of a richer, higher-dimensional reality. And that's not science fiction. That's the frontier of modern physics. Now that we've laid the groundwork, understanding what dimensions are, why physicists suspect there might be more than 3, and how those extra dimensions could be hidden, let's dive deeper into the theory that made higher dimensions not just plausible but necessary: string theory. You've probably heard of string theory as the theory of everything, a framework that promises to unify all forces and particles under one elegant set of principles. But what exactly is it? And why does it demand 10 or even 11 dimensions? At its core, string theory is a radical reimagining of what the universe is made of. For most of the 20th century, physics operated under the assumption that the fundamental constituents of reality are point-like particles, electrons, quarks, photons, infinitely small dots with no internal structure. This picture works incredibly well in the standard model of particle physics, which has been tested to astonishing precision. But when you try to include gravity in this framework, by treating the graviton, the quantum carrier of gravity, as another point particle, you run into mathematical disaster. The calculations produce infinities that can't be removed. This is because gravity, unlike the other forces, is tied to the very fabric of spacetime. At extremely small distances, near the Planck scale, the quantum fluctuations of spacetime itself become so violent that the notion of a smooth, continuous geometry breaks down. Point particles, interacting at single points in this chaotic foam, lead to nonsensical results. String theory solves this problem by replacing points with strings. Instead of zero-dimensional dots, the basic objects are one-dimensional loops or segments of energy, vibrating at specific frequencies. These strings are unimaginably tiny, about 10 to the power of minus 35 meters long, so small that even if you magnified an atom to the size of the observable universe, a string would still be smaller than a tree on Earth. Because strings have length, they don't interact at a single point. Their interactions are smeared out over a tiny region, which softens the extreme behavior that causes infinities in point particle theories. The result? Gravity and quantum mechanics can coexist peacefully. In fact, string theory doesn't just include gravity, it predicts it. One of the vibrational modes of the string automatically behaves like the graviton, with the right spin and coupling strength. That's not something you put in by hand. It emerges naturally from the math. But here's the catch. For this to work, the strings must vibrate in more than 3 spatial dimensions. Why? Because the mathematics of string vibrations only produces consistent, physically sensible results, like positive probabilities and stable particles, if the number of spacetime dimensions is fixed. Let's unpack that. In classical physics, a violin string can vibrate in many ways: the fundamental tone, the first harmonic, the second harmonic, and so on. Each mode corresponds to a different frequency and energy. Similarly, a fundamental string in string theory can vibrate in countless patterns. Each pattern determines the mass, charge, and spin of the particle it represents. But unlike a violin string, which vibrates in our familiar 3-dimensional space, a fundamental string moves through the full geometry of spacetime. Its possible vibrations depend on how many directions it can wiggle in. If you restrict it to 3 spatial dimensions, the quantum version of the theory develops anomalies, mathematical inconsistencies that violate conservation laws or allow faster-than-light signals. However, if you allow the string to move in 9 spatial dimensions plus 1 time dimension, 10 total, the anomalies cancel out perfectly. This isn't a coincidence. It's a deep requirement of quantum consistency. The number 10 arises from the need to balance the degrees of freedom in the string's motion with the symmetries of the theory, particularly conformal symmetry on the string's worldsheet, the 2-dimensional surface it traces out as it moves through time. So written out clearly, for bosonic string theory, the earliest version, which only includes force carrying particles, the critical dimension is 26. But that theory has problems like predicting a particle with negative mass squared, a tachyon, which signals instability. When physicists added fermions, matter particles, and introduced supersymmetry, a symmetry that pairs every boson with a fermion, they got superstring theory. And superstring theory only works consistently in 10 spacetime dimensions, 9 of space, 1 of time. Later in the 1990s, a breakthrough called the second superstring revolution revealed that the 5 known versions of superstring theory weren't competing theories at all. They were different limits of a single, deeper theory living in 11 dimensions. This theory was dubbed M theory. No one knows what the M stands for. Maybe membrane, magic, mystery, or mother of all theories. What's clear is that M theory includes not just strings, but also higher dimensional objects called branes, short for membranes, which can have 2, 3, or even more spatial dimensions. In M theory, the fundamental object is an M2 brane, a 2-dimensional membrane, and its dual, the M5 brane, a 5-dimensional object. Strings appear when M theory is compactified on a circle. The M2 brane wrapped around the circular dimension looks like a string in the remaining 10 dimensions. This elevates the role of extra dimensions even further. They're not just a mathematical convenience, they're essential to the structure of reality at the most fundamental level. Now let's talk about supersymmetry, because it's central to why string theory works in 10 dimensions. Supersymmetry proposes that every known particle has a superpartner with a spin differing by 1/2 unit. So the electron, a spin 1/2 fermion, would have a selectron partner, a spin 0 boson. The photon, a spin 1 boson, would have a photino, a spin 1/2 fermion, and so on. Although supersymmetry hasn't been observed in experiments yet, meaning if it exists, it must be broken at energies above what current colliders can reach. It solves several major problems in physics. It stabilizes the Higgs mass against huge quantum corrections, the hierarchy problem, allows the 3-gauge forces of the standard model to unify at high energy, and provides a natural candidate for dark matter. the lightest supersymmetric particle. In string theory, supersymmetry isn't optional, it's built in. Without it, the theory either has tachyons or fails to include fermions. And crucially, supersymmetry only closes. That is, the algebra of symmetry transformations only works consistently in specific numbers of dimensions. For superstrings, that number is 10. So the formula isn't arbitrary. It comes from demanding that the quantum theory respects both Lorentz invariance, the symmetry of special relativity, and supersymmetry. When you compute the commutator of two supersymmetry transformations, you get a translation in spacetime, but only if the dimension is 10. In any other number, you get extra terms that spoil the symmetry. That's profound. It means the dimensionality of spacetime isn't just a background stage. It's dynamically tied to the symmetries that govern physical law. Now back to compactification. If the universe has 10 spatial dimensions, why do we only see 3? The answer, as we touched on earlier, is that 6 of them are curled up into a tiny, complex shape. But it's not just any shape. It has to satisfy stringent mathematical conditions to preserve the physics we observe. Enter Calabi-Yau manifolds. Named after mathematicians Eugenio Calabi and Xingtung Yau, these are 6-dimensional spaces that are compact, finite in volume, Ricci-flat, meaning they solve Einstein's equations in vacuum, and Kehler, a condition from complex geometry. Most importantly for physics, they preserve n equals 1 supersymmetry in 4 dimensions, the minimal amount needed to avoid conflict with observation while still solving the hierarchy problem. When you wrap 6 dimensions into a Calabi-Yau shape, the way strings vibrate around its holes and curves determines the properties of particles in our 4-dimensional world. For example, the number of generations of quarks and leptons, 3 in our universe, is related to the Euler characteristic of the Calabi-Yau manifold. The masses and coupling constants arise from integrals over the manifold's geometry. But here's the challenge. There are potentially 10 to the power of 500 different Calabi-Yau manifolds. Each one gives a different low-energy physics. This vast collection of possible universes is called the string landscape. Some have no electromagnetism, some have no atoms, some collapse instantly. A tiny fraction might resemble our universe. This raises a philosophical dilemma. If string theory allows so many possibilities, does it really predict anything? Critics argue that without a principle to select our particular vacuum, the theory loses predictive power. Proponents counter that cosmological evolution, perhaps through eternal inflation, might populate different regions of the multiverse with different vacua, and we simply live in one compatible with life. Whether you find that satisfying or not, the existence of the landscape doesn't invalidate extra dimensions. It underscores how deeply geometry shapes physics. Now, let's consider a mind-bending consequence of string theory and extra dimensions, the holographic principle. This idea, born from the study of black holes, suggests that all the information contained within a volume of space can be fully described by a theory living on its boundary, 1 dimension lower. For example, a 3-dimensional region with gravity might be equivalent to a 2-dimensional quantum field theory without gravity. This isn't just analogy, it's a precise duality, demonstrated in certain limits of string theory through the AD-SCFT correspondence, anti-de Sitter conformal field theory. In this framework, a string theory in a 5-dimensional anti-de Sitter space, which has constant negative curvature, is exactly equivalent to a 4-dimensional supersymmetric Yang-Mills theory on its boundary. Gravity in the bulk emerges from the interactions of particles on the boundary. What does this mean for dimensions? It implies that dimensionality might not be fundamental. What we perceive as 3 spatial dimensions could be an emergent property of a more basic, lower-dimensional reality. In this view, extra dimensions aren't real in the traditional sense. They're part of a dual description that's mathematically equivalent but conceptually different. This flips the script entirely. Instead of asking, why are there extra dimensions? We might ask, why does our description require them? The true degrees of freedom could live in fewer dimensions, and the higher dimensional picture is just a useful tool. Still, for practical purposes in string phenomenology, the effort to connect string theory to real-world physics, extra dimensions remain indispensable. They're where the physics happens. Let's now address a common question. If strings are so small and extra dimensions are even smaller, how can we ever hope to test string theory? It's true that directly probing the Planck scale is far beyond current technology. The Large Hadron Collider operates at energies around 10 to the power of 4 GeV, while the string scale is likely near 10 to the power of 19 GeV. That's a factor of 10 to the power of 15 difference, like comparing the width of a human hair to the distance across the Milky Way. But indirect signatures are possible. We've already mentioned Kaluza-Klein particles and microscopic black holes. Another possibility is cosmic strings, topological defects left over from phase transitions in the early universe. Unlike fundamental strings, cosmic strings would be macroscopic, perhaps stretching across galaxies. They could leave imprints on the cosmic microwave background or generate gravitational waves detectable by observatories like LISA. Also, if supersymmetry is discovered at future colliders, it would be a major boost for string theory, since supersymmetry is baked into its foundation. While supersymmetry alone doesn't prove string theory, its absence at accessible energies would make the theory much less natural. Moreover, precision tests of gravity at short distances continue. Experiments using cryogenic resonators, atomic interferometry, or neutron scattering are pushing sensitivity down to the micrometer scale. Any deviation from Newton's inverse square law would be revolutionary, and a strong hint of extra dimensions. Now let's clarify a subtle point about dimensions in M-theory. While superstring theory lives in 10 dimensions, M-theory requires 11, 10 of space and 1 of time. How does that work? In M-theory, there is no string as the fundamental object. Instead, there's a two-dimensional membrane, the M2 brane. When one of the spatial dimensions is compactified on a circle, the M2 brane can wrap around it. From the perspective of the remaining 10 dimensions, this wrapped membrane looks like a string. The radius of the circle determines the string coupling strength. Small radius means weak coupling, perturbative string theory. Large radius means strong coupling, where non-perturbative effects dominate. This shows that dimensions aren't just passive containers. They actively control the behavior of physical theories. Changing the size of a compact dimension can turn one theory into another. Furthermore, in M-theory, our universe could be a three-dimensional brane floating in an 11-dimensional bulk. Open strings end on branes, so all standard model particles are stuck on our brane. But gravity, carried by closed strings or M-theory gravitons, propagates in the full bulk. This again explains gravity's weakness. One fascinating model based on this is the Randall-Sundrum type II scenario, where a single brane sits in a slice of 5-dimensional anti-de Sitter space. The warping of the extra dimension creates an exponential suppression of mass scales, so that the Planck scale on the brane is much larger than the true fundamental scale in the bulk. This solves the hierarchy problem geometrically, without fine-tuning. The formula for the warped metric in this model is the spacetime interval equals exponential of -2 times k times the absolute value of y, multiplied by the 4-dimensional Minkowski interval, plus the differential of y squared. Here, y is the coordinate of the extra dimension, and k is a curvature scale related to the cosmological constant. Because of this exponential factor, Even a modest size for the extra dimension can produce a huge hierarchy between the weak scale and the Planck scale. And crucially, this model predicts deviations in high-energy graviton production at colliders, signatures that are actively being searched for. Now, let's return to the original question with fresh eyes. Do we really live in 3 dimensions? From a phenomenological standpoint, what we measure in labs, what we see in telescopes, the answer is yes. All known particles and forces, except possibly gravity, behave as if space has exactly 3 extended spatial dimensions. Atomic spectra, crystal structures, fluid dynamics, planetary motion, all confirm this. But from a theoretical standpoint, seeking a complete, self-consistent description of quantum gravity, the answer leans toward no. 3 dimensions are insufficient. The mathematics of unification, consistency, and symmetry demands more. And here's a key insight. Dimensions might not be fixed. In some approaches to quantum gravity, like causal dynamical triangulations or asymptotic safety, the effective number of dimensions changes with scale. At large distances, spacetime appears 4-dimensional, 3 space, 1 time. But at the Planck scale, it might behave as if it has only 2 dimensions, a phenomenon called dimensional reduction. This could help tame the infinities of quantum gravity. So dimensionality itself might be an emergent, scale-dependent property, not a rigid backdrop. This brings us to the frontier of current research. Physicists are exploring whether spacetime and its dimensions are fundamental or derived from more basic quantum information theoretic principles. In entanglement-based approaches, spacetime geometry arises from quantum entanglement between degrees of freedom. More entanglement means shorter geometric distance. In this view, dimensions aren't primary. They're collective phenomena, like temperature or pressure in a gas. If true, then asking how many dimensions are there is like asking how wet is water. It depends on the level of description. At the macroscopic level, 3 spatial dimensions work perfectly. At the quantum gravitational level, the concept may dissolve entirely. But until we have a complete theory, extra dimensions remain our best guide. Let's now consider a historical parallel. In the late 19th century, physicists believed the universe was filled with a substance called the luminiferous ether, an invisible medium through which light waves propagated, much like sound through air. The famous Michelson-Morley experiment failed to detect Earth's motion through this ether, leading to its abandonment and paving the way for Einstein's relativity. Could extra dimensions be our modern ether, a useful fiction that will eventually be replaced? Possibly. But unlike the ether, extra dimensions aren't introduced to save a failing theory. They emerge unavoidably from attempts to solve deep, well-defined problems: quantum gravity, unification, the hierarchy problem. Moreover, they make testable predictions, however challenging to verify. That makes them scientific, not metaphysical. Another angle, Occam's razor. Doesn't postulating 6 unseen dimensions violate the principle of simplicity? Not necessarily. Simplicity isn't about the number of entities, but about the number of independent assumptions. String theory starts with one simple idea, a vibrating string, and derives particles, forces, and spacetime geometry from it. That's arguably simpler than the standard model plus general relativity, which require dozens of arbitrary parameters, particle masses, coupling constants, with no underlying explanation. In that sense, extra dimensions are the price of deeper unity. Now let's imagine a future where extra dimensions are confirmed. What would that mean for humanity? Practically, not much at first. We wouldn't suddenly gain the ability to travel through higher dimensions or access parallel worlds. But philosophically, it would be transformative. It would mean that reality is far richer than our senses suggest, that the universe has hidden layers, accessible only through reason and mathematics. It would also validate a profound idea. that the laws of physics are not arbitrary, but constrained by mathematical consistency. The number of dimensions isn't chosen by chance. It's dictated by the requirement that the universe be logical, stable, and capable of supporting complex structures like stars, planets, and life. In closing this second part, let's remember that science progresses not by accepting appearances, but by questioning them. Just as Copernicus showed, we don't live at the center of the universe, and Darwin showed we're not separate from nature. Modern physics suggests we don't even experience the full dimensionality of reality. Whether through strings, brains, or something yet undiscovered, the quest to understand dimensions is ultimately a quest to understand our place in the cosmos, not just where we are, but what kind of reality we inhabit. And that journey is far from over. Good night, sleep well, and may your dreams be as vast and mysterious as the dimensions we've explored.